So this is number 7 from the AB Fall Review FRQ packet. So number 7 says ship A is traveling due west. So we have A, which is traveling west, towards a lighthouse rock at a speed of 15 kilometers per hour. B is traveling due north away from the lighthouse at a speed of 10 kilometers per hour. Let X be the distance between ship A and the lighthouse rock, and Y distance between B and lighthouse rock. Okay. So then part A says find the distance between A and B when X equals 4 and Y equals 3. So the distance, I'm going to call that Z. The distance will just simply going through Pythagorean theorem. So x squared plus y squared equals z squared. So z must be 5 kilometers at this moment in time. Part B says find the rate of change of the distance between the two ships when x equals 4. So we're trying to find dz dt, right? Trying to figure out the rate of change of the in distance between ships A and B. So we're going to rely on the Pythagorean theorem. X squared plus y squared equals z squared. And we're trying to locate dz dt. So we need to find the derivative with using related rates. So x squared becomes 2x dx dt. Y squared becomes 2y dy dt. Z squared becomes 2z dz dt. Let's see if we can also pick out some information from this problem, right? We know that dx dt is going to be negative 15 kilometers per hour. And the reason why it's negative is because A is approaching the lighthouse rock, so we know that this distance is decreasing over time, so we know the rate is going to be negative. Okay. However, dy dt is going to be positive 10 kilometers per hour because the distance is increasing over time. Okay. Y is increasing over time, so 10 kilometers per hour. So we know that at the moment when x is 4 kilometers, we know y is 3, and we know z must be 5. And we know dx dt, we know dy dt, so the only missing information is dz dt. So we can plug all that information in, algebraically solve for dz dt, and we get negative 6 kilometers per hour. Okay. Part C, let theta be the angle shown in the figure. Find the rate of change of theta in radians per hour when x equals 4 and y equals 3. Okay. Now, usually with these problems, to find the rate of change, in this case, rate of change of the angle measure, d theta dt, it's not always, but a lot of times we're just having to rely on tangent to get us to that. So we want to use tangent here since we have information for these original variables, not only y and x, but also dx dt and dy dt. So we'll just go ahead and stick with the original variables. So our starting equation is tangent of theta is equal to y over x, right? Tangent of theta is opposite over adjacent, and those are the values that are given to us. Right? So we want to find the derivative with respect to time for each of these variables, and then eventually solve for d theta dt. So tangent of theta becomes secant squared theta times d theta dt. So that's the left side. Y over x, we have to go through quotient rule. So f prime g minus f g prime all over g squared. So f prime, y becomes dy dt. G, which is x, minus f, which is y, g prime. X becomes dx dt, all over denominator squared. So now we want to solve for d theta dt. We have information from part A and B for dy dt and x, of y and dx dt, and of x squared. The only thing that's that we don't know what theta is, but we do know what the trig ratio is, right? We do know what secant of theta is. Secant of theta is just going to be hypotenuse over adjacent, right? So z over x. So this is 5 over 4. So secant theta is 5 over 4. If I replace secant theta with 5 over 4 and I square that, I get 25 over 6. Divide both sides by 25 over 16, which is the same thing as multiplying by the reciprocal times 16 over 25. This fraction on the right side reduces to be 85 over 16. And 85 over 16 times 16 over 25. 16 cancels out, we get 85 over 25, which reduces to be 17 over 5. And this is in terms of radians per hour.